Welcome to this video on using net force equations to make calculations and predictions. Now, if you haven't watched videos 1, 2, and 3, you really need to go check those out, otherwise this one won't make sense. But if you just need help with this part, obviously keep watching. So we have to condense all the skills that we've developed in videos 1, 2, and 3 to now use them in this step. So let's go ahead and read what we're going to do here. We have example 1 says a 7-kilogram box is at rest on a table. With what force does the table push up on the box? Alright, well my first thing is I have to draw my free body diagram. So let me go ahead and do that. Alright, so I've got my free body diagram there. Next, I need to list out any given information that's numerical. Alright, so I have that the mass of the box is 7 kilograms. So remember from video 3, kilograms is a measure of mass. So I'm going to put here that my mass equals 7 kilograms for the box, and it's at rest on the table. That means that I automatically know that my net force is equal to 0. Okay, with what force does the table push up on the box? Well, that's the part that I'm trying to figure out, and so I'm going to put that equal to a question mark. So I'm going to put that my normal force, which is the table pushing up on the box, is equal to question mark. So you see you have to make some sort of inference here in what information is given. The fact that it told me it was at rest, that means my net force is 0. They want to know what the table is pushing up on the box. That means I'm looking for the normal force. So now I have what I've been given. The one other piece of information that's always given, so to speak, for our problems is that the gravitational acceleration or field is 9.8, which I'm going to round to 10 for my problems, and the units are going to be newtons per kilograms or meters per second squared, either way, as you remember from video 3. Okay, at this point, I'm going to assign my signs to each force. I'm going to go with my traditional where up is positive, down is negative. Okay, I'm going to write my net force summation. So I'm going to write that my net force is equal to the normal force plus a negative gravitational or minus the gravitational force. And I know that has to equal 0. Okay. Now we are at the part that's really new to us. The new part is how do I actually make the calculation of the normal force? Well, you can see here that if I can solve for the gravitational force and plug it in, then I can solve for the normal force because they add up to 0. In other words, the normal force is the exact same thing as the gravitational force. And I can solve that by adding force gravity both sides, or I could just say that, well, any two numbers that add up to 0 are the same. Okay, so let's figure out what the gravitational force is. Again, from video 3, we remember that in order to calculate the weight or the gravitational force, that's going to be equal to the mass of the object times the acceleration due to gravity or the gravitational field. So I'm going to put here the mass is 7 and the gravitational field is, I'm rounding it to 10. So that leaves me with 70 newtons. So I can see here that the normal force is really just equal to 70 newtons because the gravitational force is also equal to that. Alright, let's do this example here. This is the same basic situation. A 7-kilogram box is at rest on the table, but it's got a 1-kilogram book on top of it. With what force does the table push up on the box? So let me go ahead and first draw my force diagram and put my signs on the object. So there we go, and that's actually just copied from video 2, I think it was. Alright, at this point what we're going to do is write out our net force equation or our summation, either way. Okay, so I'm going to start with normal force minus, so that's actually normal force 1, sorry, minus normal force 2 minus Fg equals 0. Now, I skipped the part where I wrote out my givens, so let me be good and go back and write those out. Well, I know the mass is 7 kilograms. That's the mass of the box, so I'm going to call that mass 1. The mass of the book is just 1 kilogram. All right. And then I also know automatically that the net force is equal to 0 because it's at rest. I also know that acceleration due to gravity, again, for me, is going to be 10 newtons per kilogram, or meters per second squared. Do I have any other information? Nah, not really. Okay, so let's see if we can plug some things in here. Okay, this Fg is the gravitational force for the box, which I already figured out here is 70. So I'm going to put normal force 1 minus normal force 2 minus 70 equals 0. Okay, now I'm going to do a little bit of thinking. The force that the book pushes down with is the same as normal force 2, because the normal force that the box is pushing up on the book with would be the same as the weight of the book. So what I'm going to do here is say normal force 2 is equal to 1 kilogram times 10. Okay, so let me do my side calculation over here. So normal force 2 is equal to mass times gravity for the book. So that's going to be 1 kilogram times 10, or 9.8, and that equals 10 newtons. So now I know normal force 2 is equal to 10. So I've got normal force 1 minus 10 minus 70 equals 0. So normal force 1 is really what I'm looking for here. Normal force 1 is the force that the table pushes up on the box. I inadvertently know that normal force 2 is the same as the weight of the book, because that's the strength it's going to push down with. Now at this point I can solve for normal force 1 by just adding both of these to the side. So 0 plus 10 is 10, plus 70 is 80, and I see that that's 80 newtons that the table pushes up on the box. Now you can see that it's bigger than this one, which makes sense because the table has to push up harder when you put something extra on top of the book. Something you might be thinking that you could do here is you could actually combine the book and the box as a single object, and you could say that I'm really just going to draw a force diagram that has the book and the box pointing down. So I'm going to say that's the force gravity of the book and the box by Earth, and then the normal force points up. And you can see that that's just a combination of these two together, which would add up to 80 anyway, because I would have had 1 kilogram plus 7 kilograms, that was what the book was, and that would tell me that the total force gravity for the book and the box is 80 newtons, which would therefore be the same as force number 1. So you can see you can do it in multiple ways. This just takes practice, and we will do a lot of that practice to help you.